In this video, we present LaViSE, short for Language Aware Vision Scale Enhancement, for referring remote sensing image segmentation. The task is to segment exactly the region described by a natural language expression in an aerial image. Our central idea is simple. We first strengthen image text grounding early, and then keep language guidance active while multi-scale visual features are being refined and merged. This lets the model localize the referred target more reliably before mask decoding. As a result, LaViSE achieves state-of-the-art performance on both RefSegRS and RRSISD, especially on difficult cases involving small targets, dense layouts, and confusing nearby distractors. Let us start with the task itself. The input is a high-resolution aerial image together with a referring expression, for example, the tennis court on the right. The output is a single segmentation mask for the target described by that sentence. This means the model has to understand what the sentence refers to, where the candidate objects are located, and which one best matches the spatial description. In remote sensing, expressions often include relations such as left of, right of, near, or inside, so the problem is not just object recognition. It requires semantic understanding plus spatial reasoning over a large and cluttered scene. This problem is especially challenging in remote sensing. First, target scale varies dramatically. The referred region can be a very small object such as a vehicle, or a much larger structure such as a sports field or service area. Second, aerial scenes are crowded, so several nearby objects may partially satisfy the same description. Third, segmentation quality matters because thin structures, compact boundaries, and background leakage can easily change the meaning of the result. Compared with natural image referring segmentation, remote sensing more often involves stronger scale variation, denser layouts, and more complex spatial relationships. A practical method therefore needs accurate language grounding, scale-aware localization, and clean mask boundaries at the same time. This is the overall pipeline. LaViSE keeps the original segmentation stage based on the SAM mask decoder, but improves the features that reach that stage. The image branch is built on a SWinB backbone, while ECMF performs early cross-modal fusion between image and text to produce a stronger global semantic token. This token is then used as a more informative prompt representation than text alone. Next, LGHF injects language guidance into the visual hierarchy at multiple scales, so localization is refined progressively instead of only once. Finally, LaViSE aggregates those levels into one cleaner and more semantically consistent feature map. The prompt representation and visual features are then passed into the prompt encoder and the SAM mask decoder for final mask prediction. LGHF mainly focuses on localization. It first introduces explicit spatial coordinates, so the language signal has a clearer way to anchor positions in the scene. Then it fuses visual and linguistic cues at several scales instead of waiting for a single late fusion step. In other words, language supervision remains active while the feature pyramid is being built. This repeated guidance is useful when several nearby objects look similar or when the referred target is very small. By refining localization stage by stage, LGHF makes it easier to separate the true target from distractors before the final mask is ever predicted. LaViSE focuses on aggregation after localization has already been improved. It aligns multi-level visual features with language through cross-attention, transfers coarse semantic context to finer layers through a top-down integration path, and then recalibrates the fused representation with language-conditioned modulation. These steps make the final feature map more coherent across scales and less sensitive to background clutter. This is particularly useful when the referred region is large, thin, or structurally complex, because the model needs to preserve both the overall extent of the target and the local boundary details at the same time. We evaluate LaViSE on two standard benchmarks. RefSegRS is smaller and denser, while RRSISD is larger and more diverse. RefSegRS contains 2,172 training images, 413 validation images, and 1,817 testing images at 512 by 512 resolution. RSISD contains 12,181 training samples, 1,740 validation samples, and 3,481 test samples at 800 by 800 resolution. We report mean intersection over union, overall IOU, and precision at multiple IOU thresholds. In implementation, we use a SWinB backbone, a BERT language branch, and a Byte 3 large-based early fusion encoder that remains frozen during training. Together, these settings let us test both small object disambiguation and large region consistency in a fair and reproducible way. On RefSegRS, LaViSE reaches 79.67% MIOU and 84.17% OIOU. This is a 2.23 MIOU improvement over the previous best method, LSCF, which reports 77.44 MIOU. The precision scores are also strong, including 89.05 at PR at 0.5 and 45.07 at PR at 0.9. These numbers show that the method improves not only average overlap, but also the stricter cases where precise localization really matters. On a dense urban benchmark with many small targets, that is a meaningful gain rather than a marginal fluctuation. On RRSISD, LaViSE reaches 65.75% MIOU and 78.12% OIOU. This is a 1.55 MIOU gain over RMSIN, which is the strongest previous competitor on this benchmark. It also achieves the best precision from PR at 0.5 to PR at 0.8. The important point is that the improvement remains consistent on a second benchmark with larger structures, broader scale variation, and more diverse remote sensing scenes. That makes the result much stronger than a single dataset improvement and suggests that the method generalizes well across different scene layouts. This representative RefSegRS case shows the qualitative benefit more directly. The query refers to a heavy-duty vehicle, and the ground truth highlights a small target in a cluttered scene. RMSIN tends to drift to a nearby distractor, while EVF-SAM shows extra activation outside the intended object. In contrast, LaViSE remains on the correct referred vehicle and keeps a cleaner mask around it. This is exactly the small object ambiguity where stronger language-guided localization is helpful, and it matches the higher precision we observed at stricter thresholds. We see the same pattern on RRSISD. In this case, the query refers to the expressway service area, so the target is a large region rather than a tiny object. RMSIN misses part of the referred area, and EVF-SAM introduces substantial clutter into the prediction. LaViSE preserves the full referred extent more reliably and keeps the final mask cleaner. So the qualitative comparison is consistent with the quantitative gains on the larger benchmark, especially the stronger region consistency reflected in both MIOU and OIOU. The ablation study shows that the three modules are complementary rather than redundant. The plane baseline starts at 7.40 MIOU and 19.70 OIOU. Adding ECMF alone lifts the result to 37.11 and 53.05, which confirms the importance of stronger early image text grounding. LGHF alone reaches 74.60 and 79.28, showing that hierarchical language guidance contributes a large localization gain. When ECMF and LGHF are enabled together, the result becomes 74.79 and 79.41. Adding LaViSE on top of LGHF gives 78.13 and 82.76, and the full model reaches the best score at 79.67 MIOU and 84.17 OIOU. Overall, the table supports the design logic of the method step by step. To conclude, LaViSE combines three ideas in one coherent pipeline. ECMF strengthens early image text grounding, LGHF keeps language guidance active across the feature hierarchy, and LaViSE unifies the refined scales into a cleaner final representation. This combination leads to state-of-the-art performance on both RefSegRS and RRSISD, with clear gains on small target disambiguation as well as large region consistency. More broadly, the results show that remote sensing referring segmentation benefits from injecting language supervision not only at the prompt level, but throughout the visual representation. Thank you for watching this presentation.